Hey everybody, this is Larry. This is day 21st of the Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. Numbers at most n given digit set. What? Okay, given an array of digits, you can use each digit as much time as you want. Return the number of positive integers that can be generated. Okay. So the first thing that I would do is, this has to be, is whether we have to, like, whether we have to do it exhaustively or do we have to do something more intelligently, right? Here, looking at the constraints and the example cases, these are kind of problems that are a little tricky sometimes, but given that n is equal to 1 billion, it's probably you cannot do it just like brute force, right? Because there could be at least there could be all 9 numbers, not 0, but still all 9 digits, not including 0, and yeah, why do they do it with string? That's why I got a little confused. But and then now you have to figure out how to do it in a way such that you could, count them without enumerating every possibility, right? Because it's easy to do this, but and then there are going to be edge cases where they give you 100 and 1 billion, and that's nice, but if the answer is like 120, then maybe it's a little bit trickier, right? Because you can do 111, but that's about it. Okay. So, so how would we do about this, right? I have a couple of ideas in my head, but to be honest, all of them for me anyway is a bit annoying to implement, but not impossible, just annoying. So that's what I'm trying to figure out what to do. And I think the short answer with respect to the idea is just we can do it one by one, right? Or one digit by one digit, and it's just kind of annoying. I think that's why I'm trying to look for alternate ways of doing it. But maybe with more practice, it'll be less annoying, and I would just do it instead of trying to find out the things. But the idea is that, okay, for me, you can break in for given n, you can break into 2 cases, right? One is, let's say n is equal to some number like 1, 2, 3, 4, 5, 6, 7, 8, right? 9. Then you could break this down to two ways to do it, which is, one is if you could do the summation of n is less than or equal to, what is it, 1 billion, something like that. Note that I am solving this live, so feel free to watch this on 2x, fast forward, whatever you need to do, right? So yeah, so we have, for n is less than 1 billion, because then now you can do really easy math with respect to the number basis, and then this is this plus the number of digits that are, I'm trying to represent this in a clear way, which is first digit is less than or equal to 1 plus, or I guess multiply, n is less than or equal to 3, 4, 5, 6, 7, 8, 9. So something like this, right? I don't think I'm being mathematically precise right now, but I think we just kind of count right now. And so this is the answer to that. And of course, how do you calculate this? Well, now you have this recursive function where, well, the new first digit is equal to first digit is less than or equal to 2 times f of n is less than 3, 4, 5, 6, 7, oops, 3, 4, 5, 6, 7, 8, 9, and so forth. Yeah. So that's basically the way that I would think about it. Oh, and this is actually missing something. This is missing the case where, no, this is not quite right. This is if this is plus the first digit is equal to 1 times this stuff. And in this case, because this is the only case where it comes up, but you can actually break it down to first digit is equal to 0. And times 2 4 6 or times what is this, 1 billion, or maybe more precisely just 999,999,999, right? So you sum up these two, and then in this case this number is equal to second digit is equal to 0 times f of n minus 7 nines this time, plus f of second digit is equal to 1 times the same thing, because it could go all the way, right? Because this represents number from 0 to 999,999. This represents the number from 1 to 2, something like that. I'm trying to count the zeros correctly, but I might be wrong on that one. But you get what I'm trying to say. And then lastly, the second digit is equal to 2 times f of n is equal to 3, 4, 5, 6, 7, 8, 9. So maybe I did have. Oh yeah, no, this is right. And then this is just equals to this. Again, maybe I'm off by 1 9, but 1 0, 1 9, I don't know. But to 2, 3, 4, 5, 6, 7, 8, 9. Okay, so maybe one extra one. But so the idea is that the number of counts is the summation of all these parts, and this is how you would break down these parts, by breaking them into smaller pieces. So that's basically the idea for this algorithm. It took me 6-7 minutes to kind of go over it. So I hope that's understandable. But yeah, and this is just from 0 to this is just from 0 to regular whatever. I can't count. And this is actually technically the first digit is 1, right? So it's actually 1 2 3 4 5 6 7 8 9, and this is actually starting from the second digit. So technically it actually is this thing. Oh man, maybe too many zeros. So like that, right? So basically those are the summations that you're doing. Of course this goes ... more with the third digit and so forth, but that's the recursive algorithm that I would think about. This does come up a few times, so I would definitely play around and practice this for counting. Yeah, anyway, so this is just annoying, and there's a lot of potential for off by ones, which is why but it should be okay. All the digits unique. Okay, yeah, that's why I just want to double check. So, but it should be okay either way. We don't really worry about it. So digits, that's sorted, because why not? But then now let's just go. Let's have a count function. Let's start with the index, and the index is just the index of the string substring of n. So let's convert this to a string. Because we always go, as you kind of notice here, we always look at the suffix of this anyway, right? So maybe I'll play around with this a little bit, but okay. So current digit is equal to n sub index. We have to do if index is equal to length of n, then we return 1 because we got to the end. That's how I usually do combinatorics. Sometimes, but in this case, that's how I would think about it. Maybe I'll change that actually, so don't hold me to it yet. So there's the current digit. So basically now we're trying to break it down one at a time, this kind of formula, right? So okay. So 4 digit in digits, if digit is less than oh sorry, if current digit is strictly less than this, then we get this case and this case where we just take the 99999s. So how do we do that? Right? And this is just implementation. I have a couple of ways to do it. It's fine, but this is actually, you could do it with a formula. I was thinking about doing it a little bit more cutely, but basically it's the number of digits left, and because the number of digits left, you can choose any of the digits. So it's just the number of digits to the power. Oh, sorry, it's the digits available to the power of the number of digits left, right? So number, because let me just demonstrate this here. Because now let's say you have 5 digits left. Example, digits left, and then you could kind of like, you know, put them as placeholders, and then each of these, let's just say you have a selection of 3 digits, say 1, 4, and 9, because now we could put anything in there. That means that there's 3 numbers here, so three numbers here, so you multiply them, and then you get 3 to the 5th, right? So that's kind of the idea behind this. It's not a magical formula. Hope it doesn't come up that way. But yeah, so if this is the case, meaning that the current digit that we're using is one of the 1, 4, and 9. If this is strictly less than, then we could, you know, the rest of these digits, we could do whatever we want, right? So basically, all right, let's keep track of the current count. Total is equal to 0. So now total, we add that to digits left to the power of, or the other way around, sorry, whoops. Digits, the length of the digits that we can use. I say use digits in double places. You go to the power digits left, right? And digits left is just equal to the length of n minus index, maybe minus 1. Like maybe I'm off by 1, but that's the general idea, right? I'm always off by 1 on these things. Okay, so if index is 0, then yeah, we need this to be minus 1 because we don't want to count the current digit, right? So that's already factored in the total. Okay, and then else if digit is equal exactly current digit, then now we do this thing where we have to do a recursion, right? And then this is the other case where digits is, oops, I mean this is the else is if digit is greater than current digit, but then we don't have to do it because that means that it is bigger than this number, right? So you don't have to care about it. So we're ignoring that. Okay. So now in this case, we want to go total is count of index plus 1. Yeah. Because now we put the current digit is this digit is the current digit, and then we just do the suffix of it, right? So okay, so then now at the very end we just return total, we return total, and that's pretty much it. Maybe let's see if this works. It's been a while since I've solved these kind of problems, so I'm a little bit shaky, to be honest. It's not, I mean, I solved this kind of thing recently. It's just that I don't have a great mental model, a little bit out of practice, and also there's just a lot of potential by off by ones and stuff like that. So so we'll kind of see. We'll debug and learn together. Hope, you know, we'll see how that goes. Okay, well at least we got one answer correct, so that's good. But why is this wrong? And why is this returning 0, right? So by the way, the sorting is not necessary, but I always try to do it just in case, because in this case you can actually do some better math about it if you want to do like a binary search in the digits to kind of make this a different formula, but we're not going to get into that. That may be an up-solving thing. But okay, but now that's said, so so this should at least equal to 1. I think I know what I am doing incorrectly, which is that I'm forcing this to be I'm forcing this to be the number of digits that are exactly that long. I think we just need to kind of basically we're missing the case where, for example, is this a billion? Can't count. So this is a billion, but we don't count numbers under a billion. So this is okay. That means that it's this plus basically we have the same thing here where we only care about the thing. So something similar to this where the length of I minus 1 because that's the suffix of the thing, and you're free to choose the second digit. Or sorry, maybe another way to think about it is that we choose the first digit to be 0, which we cannot do it in another case, but we can choose the first digit to be 0 to kind of cascade that round. But we might still be off by a little bit as a result, but I think this should get us on the right track. So this is, I suspect this is still going to be wrong, but it should be closer. So yeah, like I said, because now we're choosing the first digit to be 0, but we're not choosing the second digit to be 0 and so forth, right? So we have to basically sum this up from all the possible digits, right? So you could say that, let's say 4 digits left in so now we're choosing how many numbers are there for 0 digit? Well, 0, but 1 digit, 2 digit, 3 digit, all the way up to digits left, or lengths of n. Yeah. Oops. Ooh. Oh, I don't. Easy fix if it's right. Okay, cool. Yeah. Well, so I mean, we're close, and obviously this is good. We're off by 1, and why are we off by 1 instead of just hacking it? We're off by 1 because now we allow things to be 0. So I think I just let 0 digits. So I think instead of just subtracting by 1, which is okay, I think if we just force this to be 1 digit, this should be okay. Yeah, which is more precise, even though you can subtract that out. Let's make sure that our 0 case is right, meaning that we have a number and like a 5 or something. I don't know. Okay, so let's give it a go. Cool. So this is definitely a hard problem if you haven't done it before. Yeah. What is the complexity, right? Well, complexity is that for each digit of n, we do this thing, but we only do, I mean, you could actually write this as a for loop if you kind of see, because there's a bit of a tail recursion here. So, and if you do it that way, then you could really see that this is just linear time, right? Or sorry, yeah, linear in the number of digits, which is actually, the number of digits is, of course, proportionate to the number of bits, which is the size of the input. So this is going to be a linear time algorithm in terms of the number of digits. In terms of space, again, linear for the same reason, linear in this number of digits, and because of the stack space. But you can actually, of course, as we just talked about, you could roll this into a for loop if you like, and that will allow you to get constant time. I do a little thing with sorting. This is actually not necessary, but yeah, and you can do this in constant space and linear time. So yeah, so again, this is a tricky problem. It's a hard problem. Don't feel so bad. Definitely practice it. I think the problem for me is that this comes up here and there, often enough that I know how to do it, but not that often that I get good practice. So even though here, actually, you've probably just saw the best version of Larry doing it, because definitely I have made a lot of mistakes in the past, just off by ones. So I think, and some of it is because on a contest scenario, I may rush it because I know how to do it. Where here, maybe because I'm, you know, talking it out loud and articulating it and making sure that all the off, you know, all the off by ones and potentials are safe. You know, it lets me solve this correctly the first time, which is good. Anyway, that's all I have. It's a technique that comes into place from time to time, doing a digit by digit calculation. I might consider doing another tutorial on this, which may be just this video, but chopped down a little bit more. Let me know what you think. Hit the like button, hit the subscribe button, join me on Discord, and I will see y'all tomorrow. Bye bye.